we've arrived at the final submodule for our CLEP course in college mathematics. This submodule studies the absolute value function. Recall the definition. Intuitively, it's equal to the distance of a number's value from 0. More mathematically, we can write it as the absolute value of x is equal to x if x is non-negative, and it's equal to negative x if x is less than 0, i.e., if x is positive, do nothing. And if you're negative, drop the negative sign. It's helpful to have both this formal definition in terms of x being greater than or equal to 0 and x being less than 0, and also this intuitive notion that it's just calculating distance between the point in question and 0. So in that sense, it doesn't matter if you're negative or positive. All that matters is how far you are from 0. So it's helpful to have an image of the plot of the absolute value of x in your mind. So let's look at a computer-generated one. So here we let the x-axis run from -5 to 5. We see that at 0, the function takes the value 0. And then for positive values of x, it looks like the line f of x equals x, which makes sense since the absolute value function doesn't do anything to positive numbers. It leaves them completely the same. Now for negative numbers, it acts by killing off the negative sign. So we would expect to see the plot of the function f of x equals minus x. And we do. This branch here that I'm highlighting in blue right now, this is f of x equals minus x. So you get the famous V shape for absolute value. We can look at what happens if we multiply it by 2 and translate. We just shift this V around. Here we've shifted down by 3 so that at the value x equals 0, I get the value negative 3. And then what does this 2 multiplier do? Well, it changes the slope of the line, right? So this line here now has slope positive 2, whereas before it had slope positive 1. So this is like f of x equals 2x minus 3. Now on the other side, the slope has changed from having slope negative 1 to having slope negative 2. So this is like f of x equals negative 2x minus 3. So let's check our understanding of the definition of absolute value in the following exercises. So I'd like to evaluate all of these functions at the same point, the point x equals 2. So here we say f of x is the absolute value of x plus 1. So f of 2 is the absolute value of 2 plus 1, which is the absolute value of 3. Absolute value function keeps positive numbers the same, so I just output the number 3. In the next example, we compute f of 2, and we get absolute value of 2 minus 7, so the absolute value of minus 5. And we recall, what does the absolute value function do to negative numbers? It kills the negative sign. So this is equal to positive 5. Here, I have negative absolute value x minus 3, so I keep the negative outside. Plug in 2 minus 3. So I have negative absolute value of minus 1. Now we have to be a little bit careful. Normally, 2 negatives would cancel, but one is inside the absolute value, the other is not. The one inside the absolute value is automatically killed off by the absolute value function. So this is equal to negative 1. These are the absolute value bars. Okay? Unlike, say, just computing negative, negative 1, in which case the negatives would cancel. Here, the first negative is already canceled by the absolute value. So we look at our last example. f of 2 of the function x, absolute value x minus 2. So absolute value 2 minus 2, so the absolute value of 0. And this is just left alone. The absolute value of 0 is itself 0. We should have some idea of how to study equations and inequalities with absolute value. All we really need to do in order to do this successfully is to recall the definition of the absolute value. So what does it mean if I have the equation absolute value f of x equals some function g of x? Well, it suffices to consider two cases. I can consider f of x equals g of x, which is the case when f of x is greater than or equal to 0. And I can look at also the case negative f of x equals g of x, which is the case when f of x is less than 0. So let's take a look at an example. If I have the equation absolute value 2x minus 3 equals 1, I have to look at two cases. I have to look at the case that the inside is positive and the inside is negative. So either 2x minus 3 could be equal to 1, but it could also be equal to negative 1. Once I take the absolute value, they'll both give me 1. So I solve these separately. So here I have 2x equals 4, so x equals 2. And here I have 2x equals 2, so x equals 1. So we check. X equals 2 gives me absolute value of 2 times 2 minus 3, which is the absolute value of 1, so 1. And if I check x equals 1, I have the absolute value of 2 times 1 minus 3, which is the absolute value of minus 1, which is also 1. Good. The last thing we want to study for absolute value is how it interacts with inequalities. All we have to do in this case is, again, remember the definition. If f is positive, the absolute value does nothing. If f is negative, it drops the negative sign. So that's what I've written here. This is just the definition of absolute value. Now, this definition is all well and good, but it looks a little bit complicated to work with. What you're most likely to see on the CLEP exam can be handled in a more efficient manner through what's called the number line method. And for this, what we do is, instead of solving the inequality directly, we first solve the corresponding equality or equation. And then we look for regions on a number line that correspond to solutions to the inequality. So instead of directly addressing the inequality, we first solve an equation and then go back and address the inequality aspect. So again, this is called the number line method. It's not as general as working with the definition, but it's easier for certain examples. So here's an example that we should look at. We have the inequality, not equality. Absolute value x plus 3 should be less than or equal to 2. What we'll do to solve this is first solve the equation x plus 3 equals 2, absolute value. So how do we do this? Well, I know that I split into two cases. X plus 3 can be equal to 2, and x plus 3 can be equal to negative 2. So the first one tells me x is negative 1, and the second one tells me x is equal to negative 5. So I've solved my equality. I've solved the corresponding equation. To get a solution to the inequality, I consider a number line as follows. So I plot my two solutions on the number line. And in each of the regions corresponding to this number line now, I check if my inequality holds there. If it holds at a single point in the region, it will hold for the entire region. This is a fact. We will not prove it, but it's the basis of the number line method. all I have to do is pick one point from each region and test the inequality. If it's true at the point, it's true for the whole region. And this will tell me the regions of solution. So let's check. Oops, I switched these. This should be, let's say, -5, and this should be -1. So let's pick a point in this region here. How about -10? So I plug in for region 1. I check -10 plus 3. Is it less than or equal to 2? Well, that's asking if absolute value of -7 is less than or equal to 2, and it's not. So this is not a region of solution. This is a region where the inequality fails. So we put a big X there. Now we can look at region 2 and pick a nice point in between -5 and -1. Let's pick -3. So we'll do that here. We'll check -3 plus 3. Is that less than or equal to 2? Well, that's if and only if absolute value of 0 is less than 2, which it is. So in this region 2, the inequality is valid. So this is a region of a solution. And we'll at last check this third region here, and we'll play the same game. We'll pick a point. We can pick, for example, x equals 0. So 0 plus 3. We ask if it's less than or equal to 2. That's if and only if absolute value of 3 is less than or equal to 2, which it is not. So this region is not part of the solution. So let's recall what we've been doing. We first solved the equation to get 2 points on the number line. Then we picked a point from each region and checked, is the inequality valid there? If the inequality is valid there, I consider that region part of my solution. If it's invalid there, I reject that region. So ultimately, what did I end up with? I ended up with just one region of solution, and it was the points between -5 and -1. So I write that out, and I include the endpoints because I have an less than or equal to. And that's the endpoint method for absolute value. It may seem a little bit delicate and tricky, but it is more straightforward from a computational standpoint than using even the definition of absolute value.